Hello everybody, this is Cal with section 5.1, Eigenvectors and Eigenvalues. So, we're into chapter 5 now. This is probably the toughest part of the course. We're only covering 3 sections in chapter 5, but they're toughies. I know that they're a lot to wrap our minds around. In section 5.1, we'll introduce the main ideas of the section, something called eigenvectors and eigenvalues. So, example 1 is a motivating example. What you can kind of see here is that we've got a matrix A, which is given we've got two different vectors, u and v. And if we hit up u and v with A, if we multiply them by A just like does something to u. But what A does to v is that it actually just stretches it out. It keeps the direction and just changes the length. And that's a little bit special. So in this case, v is going to be called an eigenvector of A. And it corresponds to what's called an eigenvalue of A, and that value is going to be the amount that A stretches V by. Let's see these as definitions. An eigenvector of an n by n matrix A is a non-zero vector x. Non-zero is very important there. So that AX is equal to lambda times x for some scalar lambda. A scalar lambda is called an eigenvalue of A if there is a non-trivial solution x of AX equals lambda x. Such an x is called an eigenvector corresponding to lambda. So eigenvectors and eigenvalues come in pairs. Eigenvectors must be non-zero. That's pretty important. And there's this equation that's governing the whole thing, AX equals lambda x. So make sure you understand those different parts of this definition. You need to know this definition before you can make any headway in this chapter. Examples 2 and 3 kind of play with eigenvectors and eigenvalues a little bit. The solution to example 3 is actually extremely illuminating. If we look over here at what happens, they take this equation, AX equals 7x, they subtract the 7x from both sides, and they pull out that x from the right side of both of those terms. And they get this equation, a minus 7i times x equals 0. And the non-trivial solutions to that equation are the eigenvectors corresponding to the eigenvalue, lambda equals 7. That means that, other than 0, the eigenvectors for this eigenvalue are a null space of this matrix, a minus 7i. And that's not a mistake. So, we call this set the eigenspace of A corresponding to that lambda, and that'll work no matter what lambda is. It didn't have to be 7. There's a warning in the middle here. We used row reduction to find eigenvectors, but you cannot use row reduction to find eigenvalues. Row reduction changes eigenvalues of a matrix. You cannot use it. We'll get into that in the next section when we discuss how to find eigenvalues for a matrix. Alright, so we have eigenvalues and eigenvectors. Eigenvectors take an n mass for a particular eigenvalue, form what's called an eigenspace of a matrix. And example 4 gives an example of finding a basis for an eigenspace. This is going to be a really fundamental skill for this chapter, finding a basis for an eigenspace. So make sure that you know how to do that in the following example 4. Theorem 1 is misleading. It is sometimes useful, but it is misleading. The eigenvalues of a triangular matrix are the entries on the main diagonal. This is only true for a diagonal matrix. You may not row reduce to a diagonal form in order to find eigenvalues. This is important. If you learn Theorem 1 as the only way to find eigenvalues, you're going to be screwed. So bear that in mind. Theorem 2 is going to be super important for us. It says that eigenvectors corresponding to distinct eigenvalues form linearly independent sets, and I'll let you puzzle that out a little bit. This is going to be really, really important for us. So give the proof a little read. It's probably useful. You don't have to worry about this section at the end about eigenvectors and difference equations. We haven't been talking about difference equations, so you can skip that little bit. So that's section 5.1.